if you want. You can just hang out in Tomato Town. Okay, so what we're looking at here, this is a C2 problem where we're looking at impulse equaling the change in momentum through a graphical analysis. What we have on the left here, kind of crudely drawn, is a force time graph or a impulse graph. And we know that the area of this kind of graph is equal to an impulse, because we know that in general an impulse is equal to a force multiplied by a time. And if force is like my height here and time is my width here, my x-axis, then force times time is an area. So if we have, some arbitrary function here like that, let's make this a little deeper. And we would like to figure out how momentum changes on this. Well, if we knew calculus, we could integrate this to find an area. And for Gigal sitting in here, like, that's what he would do if he had this function. We, on the other hand, we're not at the level of calculus yet. We don't know that. But what we're just trying to do is we're trying to find the area under this curve. Because remember, this impulse is just an area. That's all it is. So what I can do here is if I can find the area of one of these blocks, and I can count the number of blocks, well, that gives me a good estimation to the amount of area. So let's just say this goes up to 100, and let's just say this is 0.1 here. If I wanted to find the area of just one block, or the impulse of one block, because remember that impulse is the area, well, it'd be 100 vertically multiplied by 0.1, and that would give me the area of this little cube here. So 100 newtons times 0.1 seconds gives me 10 newton seconds. And that would be the impulse generated by one little block there. Now, in order to find the entire impulse, or the total impulse going on in this problem, I would need to estimate how many total blocks there are. Because if I know there's 10 newton seconds per block, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, maybe like 14. Maybe these two combined are 15, even though they're like missing a little bit, and that's probably a little much. Maybe like this and this are 16, and maybe this is like 17. I don't know, that might be a little much, might be a little less. We're just estimating here. Do your best. If I say that there are a total of 17-ish blocks, and each block is worth 10 newton seconds of impulse, just pull that down, then I know that the total impulse under this curve, the total area under the curve, is equal to 170 newton seconds. And that's just what all of this represents. That's 170 newton seconds of impulse. If I know that I have an impulse of 170 newton seconds, remember what we have just done here is this impulse, total impulse, JT, that is the quantity force times time, except a little bit more descriptive of that because this force can vary in the time. Because of this, when we set up our equation of Ft equals m delta v, or Vf minus Vi, this 170 newtons here, it is all of Ft. So what we can do is, instead of writing Ft here, we can just get rid of it and say, hey, this is the 170 newton seconds. We found it. That's the area under this curve. It was a force multiplied by a time to get that area. So now that we've found the total impulse here, if we're given something else in the problem, maybe we're given a mass, maybe we're given a velocity, whatever it is, we can kind of work around and solve for the unknown variable here. So let's just say in this problem, it's a kid kicking a soccer ball on the ground. The initial velocity of that soccer ball on the ground would be 0, so that just goes away. It's nice 0. And let's just say a soccer ball has a mass of like 0.6 kilograms. I don't know what a soccer ball mass is, but we'll just say that. If we have those values and we'd like to find what's the final velocity after he kicks it, then this is nothing more than 170 newton seconds equals 0.6 times VF minus 0. So that's just VF. And then at this point, you're just playing a division game. If you divide by 0.6 on each side, kilograms, you get 170 divided by 0.6. Whew! Kid's got a pretty powerful foot because this kid just kicked the ball at 283.3 meters per second. So I guess Arsenal will be hiring that kid to play in their games. Okay? But that's what you're doing here. You're just plugging in values. It's primarily that 117 that goes there, and we got that value just by taking, how much was it for one block, and then how many total blocks did we have. Okay? And with that, this problem is fin. Yeah, Drake, Royal Fleet definitely inbound.